nodal voltage.
Yes. All right, so.
You're 1 minute late.
Yes.
Sorry.
Yeah. We moved the class back half an hour even for you this spring, and me. But mostly you don't complain.
It took me 1 minute to walk in.
Should let him
I guess.
Okay. I was just mentioning to Joanne, make sure. I think you're doing pretty well because you have a bunch of stuff now. You're doing great, but just make sure you check both classes and see where you are in assignments and stuff. Yeah, I'm not getting after anybody. I'm just saying check. If you have a 0, that means you didn't get it turned in. Mm-hmm. And you both have access and Blackboard. You should be checking those constantly. Just going, oh, hey, you got a grade in there. Oh, hey, you gave me a 0, but I think I did that. Where is it? Yeah. Okay. I'm going to do more nodal voltages. So we did one. It was really very simple because it's a single node. But obviously, with nodal voltages, we can do more. So let's do an example here in nodal voltage. So if I have 10 volts, I have 2 ohms. Incidentally, I'm grabbing this one out of the textbook, so when you refer back to it, they do it different than me, but you at least have the numbers sitting in there. 2.5 ohms. So I picked small, well they did, but I picked small resistances here so that we could, this should be a fairly straightforward problem to work. What's that?
I had issues with one like this.
Yeah. This one I get all kinds of fun in. Now, first of all, if I were going to do this with Kirchhoff's junction and loop laws, I have 1, 2, 3 junctions and 1, 2 loops. No problem. I can write 5 equations and 5 unknowns and do lots of algebra to solve for it. I don't really want to. I can do mesh currents. I can put 1, 2, 3 mesh currents. No problem. 3 equations, 3 unknowns. I can do 2 nodal voltages though. So hey, 2 equations and 2 unknowns. So I'm going to come up here. I'm going to label this V1 and V2. So this is this node and this node. And again, that's relative to ground. So probably just assume that as a ground, make sure that I note it here. I'm also going to go through, I don't know if I need the numbers on these, but let's go ahead and split them. So this is battery 1. This is 2 ohms. 2 ohms. R1, already put the values down. R1, R2, R3, R4, R5, it's battery 2. Let me do one more thing before I start. Note my battery 2's polarity. Okay, battery 1 is the way I usually expect, right? Positive at the top, negative at the bottom. Battery 2. So I do this, I do have to make sure and keep track of battery 2's polarity. That's important. Now, when you read in the text, what they do is they do conversions of these to current sources. I'm gonna be honest, I don't really like doing it that way, so I'm gonna do it without doing that. It's an extra conversion. It gets rid of a lot of the fractions, right? But we don't need to do it. So what I can do here is I can take a look and I can say, hey, there's a node right here, right? Node 1. The currents that flow into and or out of the node. If I take a look right here, do we want to write them all as flowing out? Or do we want to write some as flowing in and some flowing out? We can do it either way we want.
I usually like put one current going down towards ground and then the other two going in.
Okay,
And that's how you did
That's
it
fine.
last time, I think.
yeah, that's
right?
fine, that's fine. I got choices though.
Okay.
So, the current that flows in here is gonna, if I look at Ohm's law, it'll be the voltage across this resistor divided by the resistance, right?
Yeah.
Which will be, the voltage across this resistor will be the voltage of battery 1 minus whatever's there divided by resistor 1. I'll come put values in, but I just wanted to do this generic to start with to make sure that, right? So the voltage across here is going to be this voltage minus that voltage divided by resistance 1. The voltage into here will be this voltage minus this voltage, the voltage on the two ends. And then the current that leaves is V1 minus 0. I will write that V1 minus 0. That's due to ground. So this is really just my current junction equation, and I just directly put in Ohm's law equations for it. Okay, I need to make sure, are you good with where I got these? Because if you don't do this part, the rest of it's, I mean, this is the hard part. After you do this, it's just algebra.
Mm-hmm.
Good, Jonah? Okay.
Yes.
And normally, if I were doing this for a problem to solve it, I would directly put the numbers in to say it understand.
Yeah.
But I want to make sure to write down this way for you to start with. So B1 is 10 volts. V1 is what I'm trying to solve for. R1 is 2 ohms. Okay, I'm just going to go and leave things in volts and ohms, and then when I'm all done, I'll get volts out. Okay, V2 I don't know. V1 I don't know. R3 is 2.5 ohms. V1 I don't know, and R2 is 4 ohms. So there's my equation. I could probably take this one further if I'd like to and get rid of the fractions. Should we do that? It'll make life a little easier. So before we move on and write the next equation, I'll just take this and go ahead and let's see. If I multiply it by 10, it seems like it, nope, it won't do it. So we'll do that. I can multiply everything by 10, and it would, it'll leave me with, we can do that. So I'm going to multiply top and bottom by 10. Is that okay?
Uh-huh.
Can I just write it outside? So I'll take this. Okay, hey, I'm going to multiply this by 10. So 10 divided by 2 is 5. So 5 times 10 is 50. 5 times V1 is 5V1. 10 divided by 2.5 is 4. So 4V2 minus 4V1. 10 divided by 4 is 2.5. That's why I made it, because it could have multiplied by 20 and not had a decimal, but I don't think it's that bad a decimal to carry around. Okay. And I don't know if it matters where I put what, but I'm going to go ahead and put all the V1s on one side. So I have minus 5, minus 4, which is minus 9, or plus 9 on the other side. Plus 2.5 would give me 11.5 V1 equals 4V2 plus 50. So I just took that equation and simplified it as far as I could. But I have one equation, I have 2 unknowns. So let's go ahead, and it might be smartest to write down the next equation before I start doing that, but I did that. So let's go over to node 2, and we're going to do the same approach. Okay, so I'm going to have this current leave because of the direction it would go through the battery. I'm going to have, you want to have this current leave too? Doesn't really matter. Same thing we've done before. If we get a negative number when we solve, it just means current's flowing the other direction. Let's see. So, it's current. Oh, all my currents are leaving here. So V2 minus V1. I mean, it's one of my assumptions is definitely wrong because all current can be leaving. V2 minus V1 over 2.5 minus, or plus, I'm sorry, V2 minus 0 over 5 plus V2. Now I want you to notice here that this is plus 4 and this is minus 4. So I'm really going to have plus 4 volts, right? I would have it negative if the polarity were flipped on that. Over 1 ohm. So that's due to my polarity. And if it ever confuses you, look and say, hey, if I were down here, I'd go V1 minus 10 over this would be my difference.
Wait. Is it, are they both supposed to add all three? Is that like equal 0?
Well, the way we drew this, all these currents are leaving.
Okay, so it equals 0?
Yep. That's why I said when I looked back at it, I'm like, one of these is definitely wrong. Because I can't have all the current leaving, but we'll find out. It'll work out in our math. All right, now I'm going to multiply by 5. So I'll take 5 times all this. So 5 divided by 2.5 is 2. So I get 2v2 minus 2v1. 5 divided by 5 is 1. 0. All right, 5 divided by 1 is 5. 5 times 4 is 20. 5 times 0 is 0. I'm going to move my, I don't know how I'm going to solve it in the end, but I'm going to go ahead and move my 2v1 over to the other side since it's negative. So I can write 2v1 equals, let's see, 2 plus 1 is 3 plus 5 is 8, v2. So I set up my 2 nodal equations. I have 2 equations and 2 unknowns, which is some algebra, definitely, but you know, it's a lot less than 5 equations and 5 unknowns, or 3 equations and 3 unknowns. I will also note, again, nodal voltages is how things like multi-sims solve their equations. So once you understand this method, you also kind of understand this is how those calculations are done. All right. I'm only drawing the box to keep things separate. It doesn't mean anything. So what is my next step is to take these 2 equations and say, well, let's solve. After doing everything I did, I think the easiest thing is to actually move everything back over to the same side and do it this way. 2v1. Well, actually, I can do it this way. I'll actually, we'll just leave it this way. I'm just going to write that one down. Now I'm going to take this equation, line it up. I can do that trick where I add equations. So I'm just going to take and multiply by minus 2 here. That way I'll get minus 8v2 and I can add those together. So this equation, what's 11 and a half times 2? 23? Seems right.
Yeah.
It's very early in the morning, so minus 23v1 equals minus 8v2 minus 2 times 50 is 100. 100. I'll bring this equation down, and I have 2v1 plus 8v2 plus 20. Add these together, I get minus 21v1 equals 0 minus 80 . So I get 80 divided by 21 is 3.095. I'll call it 3.81 volts. Look at that, I got V1. Being just slightly paranoid about my early morning mathematics. I'm pretty sure it's right. I worked it right before I left yesterday. So. I did put my solution down. Yes, 3.8095 volts. I want to stop right here and make sure you're both caught up and okay with this.
Mm-hmm. Can I take a picture of that?
Yeah, sure. And again, it's all, everything's recorded too, so feel free to, I post all these recordings after class, so you always have my lectures available to look at otherwise. I'm not done yet. I'm going to take my equation to V1 equals 8V2 plus 20. I'll put 3.81 in. I'm going to bring 20 over. So I'm going to take 3.8095 times 2. Subtract 20 from it. I'm left with minus 12.38. So V2 equals minus 12.38 over 8. Minus 1.5476. So yes, this is 3.81 volts. This is minus 1.55 volts. Those are both relative to ground. Do those make sense to you before I move on? Do a common sense check. Well, I know that 10 volts, if I go around here, I still have my loop concept. If I go around here, if I put 10 volts in, this voltage plus this has to equal 10 volts. Right? So what I was just saying, Joe, is this voltage plus this voltage have to equal 10 volts. So if that's 3.81 volts, that doesn't mean it's necessarily right, but it does mean, well, it's less than 10, and it seems like some number that's kind of sort of reasonable when you have these two, about 42. How do I find out? Oh, well, let's do this. I can take 10 minus 3.81. That'd be the voltage across that resistor, right? So this current, and divide by 2 ohms, is 3.10 amps. So again, I took 10 volts minus 3.8 volts and divided by the 2 ohms. Down here, my current, 3.81 volts minus 0 divided by 4. So it's just 3.81 divided by 4 is 0.953 amps. The way I wrote this, so the current through 3 right here. Actually, instead of getting this all messy, I'm going to write over into the board and say, right, the current that goes through 3, the current 3. The way I wrote it would be V2 minus V1 over R3, right? Because I wrote it going this way. I'm sorry. Yeah, that's right. Yeah. This voltage minus the other voltage over there. So if I were to write it out now, I can put, it all works for my numbers. This is minus 1.55 volts minus 3.81 volts, all divided by, is that 2.5 ohms? Yeah, 2.5 ohms. So what does that mean? Right? I just did the math. Now, it might be easier for me to come over here and recognize, hey, I'm going to go from 3.81 down to 1.5 minus 1.55 volts. So really it's 3.81 minus 1.55 going that way, which is all correct. But if I go back to my initial calculation, it's also all correct. I get minus 2.144 amps this direction. Or in other words, I have 2.144 amps actually going that direction. The negative sign just says, hey, my initial assumption was wrong. It's really going this way. I mean, what's happening? I have 3.10 amps coming in, 0.953 goes here, 2.144 goes there. Okay, my current here, I'm going to take 1.55, actually minus 1.55, divided minus 0 on the other end, divided by 5. So I get a current of minus 0.31 amps, which really just means my current is flowing that direction. Which makes sense, right? This voltage is higher than that voltage, so that's negative. This is 0. So I left 0 and I went down 1.55 volts, so I went across and current's flowing that way. And again, when you go down voltage, it's no different than, if you're moving along an x-axis. I left here and I went this way from 0, I went in the negative direction, this direction. Common sense check. Well, of course my current's going this way because my current's coming out of the battery here and going to go there. There's nowhere else for it to go. All right, how about here? My current, which we assumed goes away, is minus 1.55 volts minus my 4 volts, all divided by 1 ohm. So effectively it's negative, well, it's 4 minus 1.55, but minus 1.55 plus 4 divided by 1 is 2.45 amps. Again, I have 2.144 that flows in here, and I add 0.31, I get my 2.45 amps. And all these currents in here end up going the opposite direction we initially labeled them because the battery's facing the opposite direction. If I flip my battery around, it'd be trying to push current this way. This isn't a bad design, by the way. Notice our batteries are working together. This is pushing current this way, that's pushing current that way. They're actually working together. There's a resistor network between them. The resistor network here is why these collectively are called networking theory. So that's what this class is mostly about. The first half of it was, hey, review, and point new things. Second half is networking theory. Be careful. It's very tempting in 2024 to think networking theory about computer networks and all. It's not. It's about resistor networks. These are all just ways to be able to manage larger circuits and understand these voltages that are going on. Again, we could solve this with Kirchhoff's law equations, but 5 equations and 5 unknowns is frankly a pain in the ass. And it's an unnecessary one. Mesh current, 3 equations, 3 unknowns. Makes it workable. We can handle 3 equations, 3 unknowns. Nodal equations, look at that, 2 equations, 2 unknowns. So, what you're going to find is some circuits are easier with mesh currents and some with nodal equations, with nodal voltages. I'm not going to tell you that either is universally better. I will say both are better and faster than doing separate Kirchhoff's law calculations. Those are things we do early on, and you're like, hey, we can do this, we understand Kirchhoff's law, it's like the next step after Ohm's law, yay. Great, we can solve some stuff. And after that, you're like, well, it starts to become a problem because it's a lot of algebra. So, believe it or not, now we've reduced our algebra a lot. So we're done with both of those types of problems after this week. Not that our circuits aren't gonna be the same, we're gonna tackle them a little different. Next week, we'll deal with what's called superposition. We've already talked about it, so superposition, we talked about like AC and DC, that if I have DC and an AC, we can just work the DC part, work the AC part, then add them together. We can also do that with these, and we'll cover that next week, though, where we can go, hey, I can work this whole problem with battery 1 in and battery 2 not even there, just pretend battery 2 doesn't exist. Then I can work the entire problem with battery 2 in and pretend battery 1 doesn't exist, and I'm going to add my solutions together and get what's actually going on. It's a powerful mathematical tool and concept. So that's what we next week. After that, we're going to get into what's called Thevenin equivalent circuits and Norton equivalent circuits, which are also other ways to work these. You will see those terms used a lot as we move on in electronics. In fact, it won't be unusual to look up a data sheet on something and have. The Thevenin equivalent is this. Nobody expects you to sit there and work the Thevenin equivalent. It's kind of nice if you go, gee, I've heard that term before and understand what they're talking about, versus some guy's name I don't know what it means. So, really, that's where we're headed for almost all the rest of the semester. Is these types of networking equations. So yeah, it's a lot of algebra. This week's lab, build circuits, measure voltages. I'll have a lot going out that are a mixture of. You can simulate this part, and you can then build it in here, and then you can. And I'm going to have you build some on terminal strips at times, and other times circuit boards. And my whole goal of that whole mixing and matching is not to make your life more difficult, because it does make your life more difficult than if you just did what you already did. The entire goal is to make sure you're understanding my connections. You're understanding when I look at this and I build this circuit, my goal is not to make something that physically looks like this circuit. My goal is to follow the connections of where things connect. If I look at an actual printed circuit board, my resistors aren't laid out in a nice organization like this. There's a good chance they're all laid out just parallel to each other where they fit side by side. And I would have to flip over and look at the copper traces and see where the connections are. You'll notice I had some homework problems like that too. That were like all the time. And I graded one of them yesterday where it kind of ran off the rails. So we're going to make sure we stop and think about those. And in fact, has everybody gotten the mesh current homework into me? That was the one just the week before spring break. Try to get that in if you can. That should have theoretically be done but before spring break. The reason is I like to go through them and go back through them. These homeworks now, if you guys can get them into me on time, I can grade them and get them back to you. And then the next time around, I can go over them and make sure that we cover things. So I've seen consistent issues, and one of the reasons I have due dates isn't, well, for me it's easier, but also because if everybody turns them into me, I can go through them all, get it back to you, and then we can go through and look at the problems and get them all answered. So when you're handing them in at various times, it means I don't really have the opportunity to go back and revisit it as a group. So it hurts the learning of everybody if you're not like getting those in. So I'm not trying to get after you so much, just say, hey, if we can do that, then we can actually increase everybody's learning.
Well, we will do that better now, you know.
Yeah. So I'm just, like that's not aimed at anybody. Let's just say. Because it's also different problems, but no offense, I'm going to pick on you, Bodie, but you're the only one I think I have that from. So I went through and I'm like, oh, I'd like to talk about that. And I'm like, but nobody else has done it yet. So.
Yeah. Everything will be worked on today.
Yeah. So, and I'm not through it yet. So I'll cover that next time. I think this time, anything you guys need me to cover? You think you can handle these? At least get started on them?
Yeah.
Build them?
I think.
No question.
I think I need you to go over like how you got all those
Currents.
currents, because
Yeah.
fell back a little bit.
That's good. I'll talk through it. Yeah.
If you don't mind, I'm going to start on stuff I'm behind on.
That's fine.
Okay. Cool.
This is all recorded, Daniel.
Yeah.
Right now, I'm live recording
Yeah.
from Kansas City. So to get this current, I'm really just looking at what's the voltage crossed here. Use the Ohm's law. So the voltage here is gonna be 10 volts minus 3.81 volts. Those are the two voltage on either ends. Take the difference, divide by 2. So if I take 10 minus 3.81, I'm gonna get 6.19 divided by 2.
I need to go outside and grab my phone.